Dear students, today we'll see some multiple choice questions on active filters which comes under the subject analog electronic circuits. So let's start with the part 4 of it. So here question number 61, which filter performs exactly the opposite to the band pass filter? So if you see the band pass filter frequency response, you can see the frequency response like this. Say this is gain and this is frequency. Okay, so here you are having gain and here you are having frequency. So if you see band pass filter, it is a filter which will pass a band of frequencies. Say this is a band of frequencies which it is going to pass. So this is your stop band, this is pass band, and this is stop band. So let's take this as frequency 1 and frequency 2. Band pass filter is a filter which is going to pass all the frequencies which comes in the range of f1 to f2, and the frequencies below f1, the signals which are having frequencies below f1 will be rejected, and the frequencies above f2, the signals which are having frequencies above f2 will be rejected. So this is a pass band. Now here the a question is, which filter performs exactly the opposite of band pass? So if you want a opposition of band pass, then stop band should go as pass band and pass band should go as stop band. So something like this will come, something like this you can have. So here you can see that this is your gain y-axis 0, this is frequency, this is pass band, this is stop band, and this is pass band. Okay, so this is f1, f2. So here is a filter which is going to stop a particular band of frequency, that is the frequency range between f1 to f2. The signals which are having frequencies from f1 to f2 will be attenuated or will be rejected, and the signals below f1 and the signals below above the frequency f2 will be passed. So this is doing exactly opposite work of your band pass filter. So the first response is for band pass filter and the second response is for band stop filter. It can also be called as band reject filter because it is going to reject a certain band of frequency. It is going to stop a certain band of frequency, or it is going to eliminate a certain band. So A, B, C, all the options are the alternative names for the same filter, which is a band stop filter or band reject filter or band elimination filter. So here the option D will be the right answer. All of the above mentioned names will be performing exactly the opposite of band pass filter. So here you can see the explanation. A band reject filter is also called as band stop and band elimination filter. It performs exactly the opposite to band pass filter because it has two pass bands. One is below the first cutoff frequency, 0 less than f less than fl. Fl is the first cutoff frequency, and then the next pass band will be above the second cutoff frequency, that is the fh. Okay, so here you see this is an explanation for band elimination filter. So here you can see that the option D was the right answer. All the above mentioned names were the exact for the filter which is just opposite of band pass filter. So the opposite of band pass filter is band elimination filter, or it is also called as band stop filter, or it is also called as band reject filter. Then we'll go to the next question. Given the lower and higher cutoff frequency of a band pass filter, okay, so here your lower and higher cutoff frequency of band pass filter are given. So again, we'll draw the same type of frequency response. So here you can see this is gain and this is your frequency and this starts from 0. So we are speaking about band pass filter. So here the cutoff frequencies are given as 2.5 kilohertz and 10 kilohertz. So here is say 2.5 kilohertz and here you say it is 10 kilohertz. Okay, so this is your band of frequency which is passed. So here you have pass band. So here you have stop band. Here you have stop band. So this is a band of frequency which is passed by this filter and it is band pass filter. Now we have to determine its bandwidth. Determine its bandwidth means what is the frequency range of this pass band. So the frequency range of this pass band will be bandwidth is equal to 10 kilohertz minus 2.5 kilohertz. So it is nothing but 7.5 kilohertz, and 7.5 kilohertz in hertz will be written as 7500 hertz. So bandwidth is equal to 7500 hertz. So here option B will be the right answer, that is 7500 hertz. So here you can see bandwidth of a band pass filter is bandwidth, that is the higher cutoff frequency minus the lower cutoff frequency. 10 kilohertz minus 2.5 kilohertz is 7.5 kilohertz, that is 7500 hertz. So here you can see the option B is the right answer. Then we'll go to question number 63. In which filter the output and input voltages are equal in amplitude for all frequencies? So the filter which passes all frequencies is called as all pass filter. So the output and input voltages are equal in amplitude for this type of filter, which is called as all pass filter, because it is going to pass all the frequencies. So here you can see the explanation. In all pass filter, the output and input voltages are equal in amplitude for all frequencies. This filter passes all frequencies equally well. So here you can see the option A, that is all pass filter, is the answer for this question. Then we'll go to the next question, question number 64. The gain of a first order low pass filter. Okay, the gain of a first order low pass filter. Options are increases at the rate of 20 decibels per decade. Option B is increases at the rate of 40 decibels per decade. Option C is decreases at the rate of 20 decibels per decade. And option D is decreases at the rate of 40 decibels per decade. Now, this is what is the options are. And here we see that when we studied about filters, filters were classified by the falling rate. Falling rate means when it is going to fall, when the transition is there from passband to stopband. So this is passband to stopband. So passband to stopband. So this will be practically like this, passband to stopband. So this is passband, this is stopband. Now this slope is how many decibels per decade of frequency. So this is your frequency versus gain again. So here you will be having gain and here you will be having frequency. So here this is the fall off rate, which will decide whether the filter is first order filter, second order filter, or third order filter. For first order filter, the fall off rate is 20 decibels per decade. For second order filter, the fall off rate is 40 decibels per decade. And for third order filter, the fall off rate is 60 decibels per decade. Now here the question is asked for first order low pass filter. So here the option C, that is fall off rate, that is decreases at the rate of 20 decibels per decade, will be the right answer. So here you can see the explanation, the rate at which the gain of the filter changes in the stop band. So from pass band it is coming to stop band, and in stop band how it is changing, how it is falling off, is determined by the order of filter. That is, the order of filter means fall off rate. Okay. Then so far a low pass filter, the gain decreases at the rate of 20 decibels per decade for your first order low pass filter. So here you can see option C is the right answer, decreases at the rate of 20 decibels per decade. Then we'll go to the next question, question number 65. Name the filter that has two stop bands. So again, a simple question here. A filter which has two stop bands. So if you see the frequency response of the filter, so this is your gain, this is frequency, this is 0. So you have two stop bands. So two stop bands are there, and in between you are having a pass band. So this is stop band, this is pass band, this is stop band, this is frequency 1, frequency 2. So all the signals of frequencies from F1 to F2 will be passed. So the filter which has two stop bands is called as band pass filter. So here you can see the option A is the right answer here. So option A is the band pass filter. So here explanation, a band pass filter has two stop bands. One is below the first cutoff frequency and one is above the second cutoff frequency. So here you can see option A is the right answer, band pass filter. Then we'll go to the next question, question number 66. An electrical filter is what? Option A is phase selective circuit. Option B is frequency selective circuit. Option C is filter selective circuit. And option D is none of the mentioned. So whenever we speak about filters, we classify them on the basis of frequency, like low pass filter, high pass filter, band pass filter, band elimination filter. So basically, an electrical filter will be a frequency selective circuit. It will pass the desired frequency range of frequency, and it can reject the desired range of frequency. So it is a frequency selective network. So option B will be the right answer here. So here you can see an explanation. An electrical filter is often a frequency selective circuit that passes a specified band of frequencies and blocks or alternates signal of frequencies outside this band. So it will blocks or attenuates the signal of frequencies outside the band. So here you can see an electrical filter is a frequency selective circuit. Then we'll go to question number 67. Filters are classified as analog and digital depending upon their construction. You can have passive or active depending upon the components used, whether they're passive components or active components. Audio or radio, so depending upon the frequency, that is whether you are having a AF frequency range or RF frequency range. So filters can be classified as analog or digital. They can be also passive or active. They can be also audio or radio frequency filters. So here the option D will be the right answer. All of the above mentioned can be your classification for filters. So here you can see explanation. Filters are classified based on the design techniques, whether it is analog or digital, elements used for construction, whether active or passive, and operating range, whether audio frequency or radio frequency. So here option D, that is all of the mentioned, is the right answer. Then we'll go to the next question, question number 68. The problem of passive filter is overcome by what? Options are analog filter, option B is active filter, option C is LC filter, option D is a combination of analog and digital filter. So here the option is active filter. Okay. Now the output of passive filter will be very low in magnitude. So if you are having an active component in it, it can amplify that output and you can get a better output as compared to passive filter. So the option here, the problem of passive filters is overcome by using active filters. Also, active filters will give you a chance of using capacitors as feedback, and then it can eliminate the use of inductors, which can be heavy and bulky. So here you can see the explanation. The active filters enclose as a capacitor in the feedback loop and avoid using inductors. This way, inductorless active filters are obtained. And also, the other point is active filters output will be higher than the passive filter output in magnitude. Say, for example, output voltage. So it will be more in terms of active filters because active filters can amplify the output, whereas passive filters cannot amplify the output. So here you can see option B is the right answer, active filter. Then we'll go to the next question, question number 69. Ideal response of a filter takes place in what? Ideal response of the filter means the output is existing. The output is having a proper gain. Okay, the output is existing. There is output voltage, and that can happen in pass band frequency. So when we say pass band frequency, whatever inputs you are applying, all those are passed in the pass band of the output. So the ideal response of filter takes place in option C, pass band frequency. So here you can see the explanation. The ideal response indicates the practical filter response and it lies within the pass band frequency. So here option C, that is pass band frequency, is the right answer. Then we'll go to question number 70. A dash filter rejects all frequencies within a specified band and passes all those outside this band. So this is again, you can see the response, frequency response, that is your gain versus frequency. And you can now what is given in the question is the filter is one which rejects all the frequencies within a specific band, specified band. So it is going to reject. So it is going to reject the frequencies between a specific band. So F1, F2. So this band is rejected, and before F1 everything is passed, and after F2 everything is passed. So this is pass band. This is also pass band, and the in between band which is rejected is stop band. So this is a frequency response of band stop filter, or it is also called as band elimination filter, okay, or it is also called as band reject filter. So here option D will be the right answer, band stop filter. So here you can see option D is the answer for this. Then we'll go to question number 71. The bandwidth in a dash filter equals the critical frequency. So bandwidth in a filter equals to the critical frequency. So critical frequency here will be the cutoff frequency. Again, if you see the response, frequency response, so this is gain and this is frequency 0. So if you see, this is pass band and this is stop band. This is pass band and this is stop band, and this is your cutoff frequency. So here the bandwidth in a dash filter equals to the critical frequency. Now this cutoff frequency is your critical frequency, and this will be the bandwidth. This will be the bandwidth. So this concept is for low pass filter. So here the option low pass filter will be the right answer. So here you can see the bandwidth in a low pass filter equals to the critical frequency, that is your cutoff frequency. Then we'll go to the next question on the same lines. A low pass filter has a cutoff frequency of 1.23 kilohertz. Determine the bandwidth of the filter. So as we have told earlier, whatever a cutoff frequency is there for low pass filter, that only will be its bandwidth. So if the cutoff frequency is 1.23 kilohertz, then the bandwidth also will be 1.23 kilohertz. So here option B will be the right answer. So 1.23 kilohertz. Then we'll go to the question number 73. A dash filter significantly attenuates all frequencies below FC and passes all frequencies above FC. So here it is going to attenuate, it is going to stop all frequencies below FC. Okay, so here if you draw the response, so this is your gain versus frequency, this is 0, and here is your frequency, that is the cutoff frequency FC. So it is going to attenuate all frequencies below FC and passes all frequencies above FC. So it is attenuate means it is going to stop band, and this will be your pass band. So this is how it is going to look, and this is a response for high pass filter. It is going to pass all the frequencies above cutoff frequency. So here the option high pass will be the right answer. So here you can see answer B will be the right answer, high pass. Then we'll go to see question number 74. A dash filter passes all frequencies within a band between the lower and the upper critical frequency and rejects all others outside this band. So it is going to pass frequencies of certain band, and it is going to reject all the frequencies outside the band. So that is nothing but again band pass filter. So option C is the right answer here. Band pass filter is the right answer. Then we'll go to the question 75. A band pass filter circuit can be created by cascading a high pass filter and a low pass filter, whether this statement is true or false. Okay, so here it is true because you can have a band pass filter by putting a low pass filter and high pass filter in series. So if you have the block diagram, you can see that if you are having a low pass filter and a high pass filter, okay, high pass filter, then this combination can give you a band pass filter. This combination can give you a band pass filter. So here the frequency response if you draw, okay, so here frequency response if you draw for band pass filter, okay, so this is your band pass filter, this is gain, this is frequency, this is 0. So this will be your stop band, this will be your pass band, this will be your stop band. Okay, now here you can see this will be the cutoff frequency for high pass filter, and this will be the cutoff frequency for low pass filter. Low pass filter. Okay, so here this is the cutoff frequency of low pass filter, and this is the cutoff frequency of high pass filter. So you can have like this, you can have a low pass filter which can pass all the frequencies, say above certain, uh, which can pass all the frequencies below a certain cutoff frequency. So this is low pass filter, a cutoff frequency. So it is going to pass here, it is going to stop here. So you're going to have something like this. Then, and here you can use a high pass filter. So here high pass filter, after cutoff frequency. So it will stop here and pass here, and this will be having your cutoff frequency for high pass filter. So if you have this in series, a low pass filter and high pass filter, you can form a band pass filter. So this option is true. So option A is the right answer. So option A, that is, this statement is true, that by a cascading high pass filter and a low pass filter, you can build up a band pass filter. Then question number 76, we can have active filters are usually fabricated by what? So here options are L circuits, that is inductor circuits, or RL circuits, or RLC circuits, resistor, inductor, capacitor, or op-amp circuits. So we know that op-amp is an active component. So active filters are usually fabricated by op-amp circuit, that is operational amplifier circuits. So here option D will be the right answer. Then we'll go to the next question, question number 77. The region between the pass band and the stop band is called as what? So if you see the region between the pass band and stop band, so again you can see a response. So here, this is gain, this is frequency, this is zero. Say for example, this is pass band and this is stop band. So this is pass band, this is stop band. Now the region between the pass band and stop band, that is this region ideally, or this is what is practically, this region is going to come from a higher state to a lower state, or it is from the upper level to the lower level, or it is decreasing. So this is called as transition. This is called as transition. So that is, the region between the passband and stopband is called as transition. So option C will be the right answer here. Transition. Option C. Then we'll go to the next question, question number 78. Which filter type is called as flat filter? So a filter in which the passband also is very flat and stop band also is very flat. So those filters are nothing but the Butterworth filter. So here option B will be the right answer. In Butterworth filters, whether it is low pass filter or high pass filter or band pass filter or band elimination filter, it is called as flat filter because the pass band and stop bands are very flat. So here explanation, the key characteristics of the Butterworth filter is that it has flat pass band as well as stop band. So it is sometimes called as flat filter. So here option B will be the right answer, Butterworth filter. Then we'll go to the next question, question number 79. Determine the order of filter used when the gain increases at the rate of 60 decibels decade on the stop band. Okay, so here stop band to pass band, if you're going to go, then it is going to increase. If you're coming from pass band to stop band, it is going to decrease. Now when the rate is 60 decibels per decade, okay, when it is 60 decibels per decade, it is third order. Okay, so here uh, 20 decibels per decade is first order, 40 decibels per decade is second order, and 60 decibels per decade is third order. Now here he has said that determine the order of the filter used when the gain increases at the rate. So from stop band, it is going to go to the pass band. That means it is a high pass filter. So option B will be the right answer here, third order high pass filter. So the gain increases for high pass filter. So for a third order high pass filter, the gain increases at the rate of 60 decibels per second in the stop band until that frequency is equal to the cutoff frequency. So here you can see the option B, that is third order high pass filter, is the right answer. Then we'll go to the next question, question number 80. Why inductors are not preferred for audio frequency? Now for audio frequency, inductors are not preferred because of the option, they are very large and heavy. They are very bulky, so large and heavy. That is why inductors are not preferred for audio frequency. So here the option A will be the right answer, that is large and heavy. So here at audio frequencies, inductors become problematic as the inductors becomes large, heavy and expensive. That is why they are not used. So here the option A is the right answer, large and heavy. Thank you, students.